Great. So let's welcome our next speaker, which is Ankur Khurana from the University of Bristol, also from the group of Stefano Valle. So welcome, Ankur, talking also about transduction. Really looking forward to your talk. Over to you.
Thank you. And thank you, BQIT organizers, for giving me this opportunity to talk about my topic, integrated phononic-photonic circuits on gallium arsenide as a platform for microwave to optical signal transduction. Many applications require fast and efficient phase modulators. For example, in data communication, for encryption protocols, laser frequency stabilization systems, terahertz optical frequency comb generator, and so on. But with recent advances in quantum technology and cryogenic devices, there have been significant constraints been put on modulators' conversion frequency, power, and efficiency. For example, in this publication from IonQ's 11-qubit quantum computer, where they're using this multi-channel acousto-optic modulators to modulate the frequency and amplitude of the diffracted beams to generate single qubit rotations and XX gates. And now as the system becomes larger and more complex, it will be indispensable to have efficient AOMs on a scalable platform which are capable of performing at cryogenic temperatures. Similarly, for Google's quantum computer, as the number of qubits increase, so does the number of coaxial cables required for microwave readout. In the future, we hope that these qubits will be read out optically via microwave to optical transduction. Also, microwave to optical transduction will also be useful to create quantum networks with optical channels, but with a solid state or an ion trap or a superconducting platform acting as a node. So the working principle of the modulator is based on the fact that an optical mode traveling along a waveguide will acquire some phase along its optical path. And since changing the path length of the optical mode is not so convenient, if we can change the effective refractive index of the material, we can produce a phase change. And most modulators are designed based on some resonant cavities because these allow for higher efficiency and lower power consumption modulators, since the resonant-based cavities make these modulators very sensitive to any change in the refractive index. The change in the refractive index can be brought about by various effects, and this gives us various different types of phase shifters. For example, in thermal phase shifters, applying an electrical field to a resistance-based heater changes the refractive index of the waveguide. In a MOS capacitor-based modulators, changing the carried concentration around the waveguide changes the refractive index. Electro-optic modulators are based on nonlinear effect within the material, like second-order Pockels effect or third-order Kerr effect. And acousto-optic modulators, they're a bit different, that they convert the RF field using an interdigital transducer to an acoustic wave on a piezoelectric material. And this surface acoustic wave, in turn, modulates the refractive index of the waveguide due to the moving boundary effect, photoelastic effect, and the electro-optic effect. Now, these IDTs, interdigital transducers, are basically periodic strips called fingers of metal on the surface of a piezoelectric material with alternate fingers connected to signal and ground bus bars. Now going back, thermal phase shifters are not power efficient, and the conversion frequency of these modulators is not high. For MOS capacitor-based modulators, even though conversion frequency is high, their performance at cryogenic temperatures is questionable. Now, electro-optic modulators and acousto-optic modulators, they provide high conversion frequency and power efficiency, and in theory, they perform at cryogenic temperatures, but acousto-optic modulators have some other advantages. For example, if we have to generalize coupling efficiency for any modulator, it can be written as a volume overlap integral of the pump signal, the RF signal, and the sidebands with some coupling coefficient C. Now, if we want to increase the coupling efficiency, we can either increase the pump and the RF signal individually, or we can increase the overall overlap integral. But in the acousto-optic modulators, they inherently allow us to do both. So because the RF field is being converted to an acoustic wave, it allows for much higher quality factors, which can be greater than 1,000 at frequencies higher than 2.5 gigahertz, whereas RF quality factors are barely around 100. Also, if you look at this table on the right, an RF field at a frequency, say 2.3 gigahertz, has a speed of light and gives a lambda, which is 13 centimeters. But at the same time, an acoustic field at 2.3 gigahertz has a velocity 5 orders less than speed of light and has a wavelength around 1.5 microns, which is very close to the optical wavelength of 1.55 microns used in telecom. This allows for much larger spatial overlap between acoustic wave and the optical wave. Also, acousto-optic modulators, they perform at cryogenic temperatures. This has been shown before. But not only that, the mechanical acoustic performance actually increases when at lower temperatures because lower thermal noise and lower acoustic phonon attenuation. Another advantage we can get from AOMs is that it can allow action at a distance, that we can place metal far away from the waveguide, which can minimize the optical scattering losses. Now, for selecting our material, if we look at this table here with some favorable properties for an integrated platform, 3.5s check most of the boxes such that they have a high refractive index, they provide direct band gap, Chi2 nonlinearity, piezoelectric coefficient, and ability to grow dots, strains, and wells. On the other hand, silicon has a high refractive index, but is not direct band gap. It's not Chi2 and doesn't have a piezoelectric coefficient. And on the other hand, lithium niobate is an insulator, has a low refractive index, but has a Chi2 and a piezoelectric coefficient. And the table on the right, if we look at some of the 3.4s here, gallium arsenide, even though has a small electromechanical coupling, has a very large optomechanical coupling. This can also be seen from the effects that account for the acousto-optic interaction. So 3 effects mainly account for that. Moving boundary effect, in which the acoustic wave produces some displacement in the boundaries of the waveguide. Photoelastic effect, where the electric field, the acoustic wave produces a strain within the waveguide, and the piezoelectric effect, where the electric field of the wave changes the properties of the waveguide. Now, for gallium arsenide, the piezoelectric coefficient is low, and the piezoelectric and electro-optic component of the doesn't account for much. It's almost negligible. But if we look at the moving boundary and especially the photoelastic contribution, the change in the refractive index for photoelastic scales as n to the power 5. So having a large refractive index produces a very large change in refractive index per phonon. That is why we have chosen GaAs as a material, because it has a very high optomechanical coupling, but is also a semiconductor and allows us to do more on the photonic side as well. So the design of our modulator is based on an unsuspended waveguide on a suspended gallium, which is firing an acoustic wave on a suspended gallium arsenide ring resonator. And we have chosen a suspended platform because it allows us to make similar designs and similar sizes like SOI, because it becomes, gallium arsenide has same refractive index as silicon, and on air, you can design the structures much smaller. So the fabrication, we start with a wafer, which is gallium arsenide substrate, which has 1 micron of aluminum gallium arsenide on top and a 220 nanometer of gallium arsenide, similar to an SOI wafer. And the crystal axis orientation matters in case of acousto-optic interaction, because the acoustic field, the speed is different in different directions. So we want to have the highest possible RF to acoustic conversion, which happens for 110 plane direction for a 001 wafer. So the first we quote spin coat PMMA, which is a positive tone E-beam resist, and then following E-beam lithography and the resist development, we deposit chromium and gold on top using thermal evaporation. After the resist liftoff, we get our IDTs and the metal on the gas substrate on the top of the 220 nanometer gas. For the photonics, we have use a negative tone E-beam resist, which is HSQ, and we have to protect our IDTs because we use argon chlorine plasma, which affects gold. And we also define our waveguides and etch windows through which we will do the wet HF etching of the underlying aluminum gallium arsenide. So the first step is doing a 70 nanometer partial etch for the grating couplers. Then using a very similar process again, but this time protecting the grating couplers, we do another 50 nanometer etch, which defines our RIP waveguides. And then there's another step of lithography involved in which we finally protect our waveguides with HSQ and open and etch the gas to 220 nanometers to open these windows to undercut the underlying aluminum gallium arsenide. And finally, we use wet HF etching of aluminum gallium arsenide to suspend our structure. So this is the fabricated design of an IDT. Since gas has a low electromechanical and piezoelectric coefficient, we have to use very large number of finger pairs, and that's why this design, because of the large size of the IDT, it wasn't feasible to release the IDTs as well or suspend the IDTs. So this is the complete device with grating couplers, suspended RIB waveguides, suspended microring resonator, and the IDT. So some of the suspended images, SEM images of the suspended structure. In this structure, we can see that the IDT is coupled to the ring resonator, and we have designed this ring resonator to accommodate for the maximum coupling between the ring and the acoustic wave, and a suspended grating coupler. So there are a few challenges when it with the fabrication. So one of the challenges, if the grating coupler is not fully undercut, which can happen, we can get a lot of losses in the grating coupler. Another issue is we use this wet HF etching and some cleaning process afterwards, which affects the acoustic response of the IDTs. So we have come up with kind of a compensation right now, which still gives us a loss in the acoustic wave, but it allows us to at least the device to work. On the experimental setup, we have a tunable CW laser coming through one of the grating couplers, and the output of the grating coupler going to a high-speed photodetector, which goes to port 2 of a vector network analyzer. And the port 1 of the vector network analyzer goes to the IDT to provide the RF signal for our IDT. So on the measurement side, we do two types of measurements called S11 and S21. S11 provides the acoustic response or how much of the RF signal has converted to the acoustic wave and the quality factor. And for our device, we got a resonant mode at 2.47 gigahertz with an acoustic quality factor of 378. Now the acoustic quality factor reduced because of this wet chemical etching, because this affects our metal somehow. And the optical response was chosen at 15, 17 nanometers because of the high quality factor of 15,000. And for our device, when we measured the S21 spectrum, we got the half-wave voltage of about 0.22 volts centimeters. So these are some of the measurements combining S11 and S1, and also shows the second graph shows when we scan the laser at different wavelengths along the slope of the resonance and measure our S21, which shows that there is modulation going on. So our next step is basically to improve the fabrication imperfections that are there right now to reduce our losses. And we want to move to quantum mode design IDTs, where we want to suspend our IDTs as well, because in this way we can reduce the losses in the substrate of the acoustic wave and get a V, and the simulation suggests we should get V by less than 100 millivolts. And we are also looking into traveling wave design of the modulator, in which the acoustic wave and the electric field within the resonator should be phase matched. So right now these are orthogonal to each other, but we want to reach a regime where they're phase matched, and then the efficiency can be significantly improved. So finally, I want to acknowledge my people who have helped me with this: Krishna Balram, Pizu Zhang, Stefano Vale, and Laura Kling. Thank you for your time.
Thank you very much, Ankur. So we only have a minute or so for questions, if there's any questions from the audience. Otherwise, maybe I'll ask a question just in a minute. If you can talk a bit briefly about gallium arsenide as the platform, and whether it's challenging to look at these new fabrication techniques and scale them up with current kind of foundry capabilities that there are in the UK and beyond.
So this platform has been designed in our own clean room and with Pizu Zhang and Krishna Balram. And these are the first active devices coming from Bristol in terms of any new platform. And so I think we are still improving the process, but there's already a publication where we have shown the passive devices with very low loss in the grating couplers and waveguides. The quality factors can reach up to 30,000. So, but in the next step, we want to go to more photonic crystal designs and different kinds of active devices also. So it gets a bit challenging when you add more layers to it or more different things. But I think we can do it. It just takes a bit time.
Indeed. Thanks a lot, Ankur. Really nice results and talk.